Thanks a lot for the opportunity to speak in this seminar. So the talk will be about sort of generalized notions of semiadditivity in several contexts. One of them is equivariant homotopy theory. And I want to start by sort of motivating, like giving sort of the main examples of this framework that we're going to introduce. So first recall what it means to be semi-additive in the ordinary sense. So I'm going to work with infinity categories. So let C be an infinity category. Recall that C is called pointed if it admits an initial object and the terminal object. And the canonical map from the initial object to the terminal object is an equivalence. And once we have a notion of, once we have a pointed infinity category, we can ask it to be semi-additive. Which means it has finite coproducts and it has finite products, and these agree with each other. So once you are pointed, you can write down a canonical map from X disjunct union Y, which is the coproduct to the product. So by the universal properties, we have to specify 4 components of this map from X to X, Y to X, etc. And we do that by taking the identity on X, the identity on Y. And then the other 2 maps off diagonal are just the 0 map, the one that factors through the terminal object, which is also initial. And the nice thing about this is that this is just a property we can ask about a category, but it provides us a lot of structure.
How is that different from additive?
Additive means that the resulting commutative monoids that you get, the enrichments, are actually commutative groups. So once you're semi-additive, you will automatically get an enrichment in commutative monoids. Roughly speaking, F plus G will be given by first taking the codiagonal, first the diagonal, you go to X times X, and then you take F times G to go to Y times Y, and then you use that this is equivalent to the coproduct, and then you take the codiagonal to go back to Y. So this gives you the enrichment in commutative monoids, and if these are commutative groups, then it's called additive. So basically you have inverses with respect to this addition. So if you're a C, what happens to be a 1 category, then we can just write down this structure by hand. But if you're working with infinity categories, it can be difficult to write down this coherent structure of a commutative monoid. So it's very convenient to have this sort of theorem that says, okay, you get it for free in the semi-additive case. And what I want to explain today is like a very large generalization to a bunch of different settings where we also get additional structure for free. So before I will explain the general formalism, let me give some of the main examples of this. So maybe, we are in a conference on equivariant homotopy theory, so let me start with that one. So you're probably familiar with the fact that if we have finite groups H and G, and we have some H representation, then we can induce it up to a G representation by just taking a direct sum over the over the cosets G mod H, and there is a certain action on this which takes into account the H action on V and the G action on this quotient. And this is so what is special about this is that it is both a left and a right adjoint to the restriction functor from G representations to H representations. And this phenomena doesn't only happen in representation theory, it also happens in equivariant homotopy theory. Oh, now I have to hide the board. That's not convenient. How can I do that? Sorry. So if we are replacing representations by genuine G spectra, the left adjoint to restriction is called induction, the right adjoint is called co-induction, and then there is again an isomorphism which is called the Witmüller isomorphism. And from this data, you get also enrichment on these categories. And instead of commutative monoids, there will now be Mackey functors. So you have, for every coset, you will get an abelian group, and there's a bunch of restrictions and transfer maps that you get from it. And a nice formalism for this was written down by Barwick, Dotto, Glassman, Nard, and Shah. Who formulated the notion of G semiadditivity. So instead of a single infinity category being G semi-additive, you need a whole family of indexing of categories that remember sort of the H equivariant object for every subgroup H of G. So you have to work with parametrized higher category theory. And then you can define what it means. I will say later, give a precise definition of this in a more general setting. And in that case, they showed that you get automatically Mackey functor enrichments. A second example comes from higher semi-additivity. In chromatic homotopy theory. So to motivate it, we might look at G, again, a finite group. And now we take V, a complex representation. Then we can consider the quotient to the orbits of the representation, and we can consider the fixed points. And there's a canonical map that sends V to the sum over the whole orbit of V. And this is an isomorphism. So it's another instance of a certain left adjoint. Quotient is left adjoint to giving some vector space a trivial action. And this is the right adjoint, and they are isomorphic. The only thing that we need is that the order of G is invertible. For concreteness, I chose C. And this has been generalized to, so I mean, you can do this for like rational spectra, for example, but it works even more generally for in chromatic homotopy theory, where we take K and local spectra.
Well, what kind of quotient is it? If you think of V as like a affine space, the quotient is no longer linear.
It's co-invariant.
Should I write it like this? It means, yeah, co-invariant. It's not a set level quotient. That's right. Yeah. Okay. It's sort of the co-limit over BG in the category of. So there's a theorem that says, I have to remember, I think it was proved by Hovey, Sadowski, combination of Hovey, Sadowski, and Greenlees. That says that if we are now taking a G equivariant object in the category of K and local spectra, which I'm going to write as a functor from BG into K and local spectra, then the homotopy orbits are equivalent to the homotopy fixed points X. And this has been generalized by Hopkins and Lurie, where we replace BG by an arbitrary pi finite space. The theorem So given a pi finite space, which means that all the homotopy groups are finite and it has finitely many path components, and given an A-indexed family of Kn local spectra,
There are only finitely many non-trivial.
and there are only finitely many non-trivial. Finitely many, yeah, thank you. Then for any functor into Kn local spectra, the colimit over A of x is equivalent to the limit over A of x. And again, once you have an infinity category that satisfies sort of the condition like this, you can show that you get a canonical enrichment in a certain kind of generalization of commutative monoids. So this was by Harpaz. Yeah, maybe I won't define right now what this means, but roughly it means you cannot only add finitely many things together, but you can add things indexed by any m finite space inside your monoids. So this is another instance where a property on an infinity category gives you this additional structure. And maybe very briefly, I want to mention a third category, which is fixed functor formalisms.
Sorry, in the previous, what is M?
Can you say again?
But what is M?
So what you can do is you can ask this property only for pi finite spaces which have homotopy groups up to level m and nothing higher, and then you will get a commutative monoid structure which sort of deals with only these kind of spaces. In principle, you can, yeah, it's not super relevant, but like it's sort of the truncation level. Okay, so let me just be brief about this and illustrate this by just giving one example, which is the fixed functor formalism of sheaves on topological spaces. So if we have a finite covering map of topological spaces, then we can consider the functor that it induces on sheaves, the pullback functor from sheaves on Y with values in spectra to sheaves on X with values in spectra. And this admits both a right adjoint and a left adjoint, which I'm going to call lower freq and lower star. And then the claim is that in the case of a finite covering map, these two maps are sort of canonically equivalent to each other. And from this, what you can obtain is enrichments in sort of sheaves with transfers. You get additional structure. For any finite covering map, you will get certain transfer maps. So what I would like to explain is sort of a formalism that deals with each of these notions of semiadditivity. And it's a variation of basically the formalism of ambidexterity that Hopkins and Lurie defined. So let me explain how that works. Right, so this is 2, I guess. So in the paper by Hopkins and Lurie, where they also proved that theorem, they introduced a general framework of ambidexterity, which sort of says we have certain functors and then it provides ways of inductively constructing certain comparison functors between the left adjoint of f upper star and the right adjoint, which we can ask to be equivalences. So let me explain how this goes. And I will sort of take a slightly different perspective on it than they write it in their paper. So what we're going to consider is we have some indexing category.
Sorry, what was the question?
Yeah, so you would like to phrase certain left adjoints are equivalent to certain right adjoints, but you would like to phrase this in a way where there is already an a priori map, and the formalism sort of gives you these maps inductively defined. That's what I'm gonna explain. So we start with some indexing category, which can be, so okay, for example, for ordinary semiadditivity, it's just going to be the category of finite sets. For G semiadditivity, it's going to be the category of finite G sets. You can do some global variations of this. Here you would take something like pi finite spaces, and here you would maybe take something like topological spaces. So, and then we are going to consider a functor that assigns to every such an object some infinity category. And in practice, we usually require it to satisfy certain limit preservation conditions. For example, to get ordinary semiadditivity, we would just consider the functor from finite sets to that infinity, which takes a finite set and sends it to c to the power s for a fixed infinity category C. So this is the same as asking for functors that preserve finite products. And then the third ingredient we need is sort of our choice of maps along which we want to have transfers. So we're going to ask for some Q inside A. This is a wide subcategory. By wide subcategory, it needs to contain all objects. So basically what I mean is I choose a collection of morphisms in A, and I'm asking it to be closed under base change. And now I would like to ask for the property that this C admits all the left adjoints for maps in this collection Q, and for right adjoints, and they need to be equal. And in order to even phrase this, I need to make an assumption on this Q. It needs to be well behaved in a certain sense. So I need it to be what we call inductible. So we say that Q is inductible if it satisfies the following properties. First, for a morphism in Q, also the diagonal is in Q. The diagonal of such a morphism is the map that goes from A to A times over B with A. So basically I'm asking that Q is closed on the diagonals. And this allows us to start the induction. I mean, this allows us to we are going to define something for Q by defining it in terms of something for delta Q. So we better make sure that this process ends after finally many steps. And this is the second condition that says that every Q is n truncated. So every morphism Q is n truncated for a certain number n.
Sorry, just checking I'm understanding this correctly. So A is now overloaded, so the definition is not saying that the category A before.
Yeah, so the notation is, this is curly A, Yeah, maybe I shouldn't have chosen the A. This, yeah,
Thank you.
there's a curly A and there's a not curly A.
Curly A has like finite limits.
Curly A needs to have pullbacks along morphisms in Q. It doesn't necessarily need to have all finite limits. I guess in practice it usually will. But it's not required for the framework to work. And this N, yeah, it may depend on Q. So what this is just saying, if you don't know what truncated means, it just means that if you do this iterated diagonal construction a bunch of times, at some point it becomes an equivalence. So that's the relevant condition that we need in this formalism. Okay, so with these two conditions, I claim that I can make precise this condition over there. So let's see how we would do that. So we say that C, this choice C that we had over there, is Q semi-additive if for every morphism in Q, the pullback functor that we have, so this is contravariantly functorial, so it defines a functor from CB to CA. This needs to have a left and a right adjoint. And then we need some compatibility conditions with pullbacks, which is, let me call it base change. It means if you have a pullback square with the vertical morphisms in Q, then you have a compatibility with the lower shriek of the one Q and the lower shriek of the other Q. So they have to satisfy this base change condition. And then we further ask that the norm map, which I will say in a second what it is, from this left adjoint to the right adjoint is an equivalence. And it's in this construction of the norm map that we will need these conditions on Q. So how are we going to construct this norm map? So we can proceed by induction, because every Q is n truncated for some n, we can just do induction on the truncation level. If it is an equivalence, then both Q lower shriek and Q lower star are just inverses to Q upper star. And then we just choose it to be the canonical identification that you have. So let's now assume that it's not necessarily an equivalence, but at least we have the structure already for the diagonal. So we're going to assume that we already have the norm map, the diagonal, and also that it's an equivalence. And then we can construct the norm map. So by moving over this Q lower star to the left, I have to give you a map from Q upper star, Q lower shriek to the identity. And to do this, okay, let me draw some diagram. So I consider the pullback of this morphism Q along itself gives me A times B, A times A over B. And here you have the projection map, here you have another projection map, and then we have the diagonal of Q. And then this is the identity, and that's also the identity. Oops, no, I don't have space here. Okay, so this base change condition says that lower shriek and Q upper star is the same as doing projection 1 upper star, projection 2 lower shriek. This is going to be the same as and now I can use that the left adjoint for delta is the same as the right adjoint. So in particular, I have a unit map from the identity to delta lower shriek, delta upper star, which I can plug in. So here we can put in the delta lower shriek, delta upper star, and then projection 1 upper star. And now we see that here we get the lower shriek for delta combined with the projection map. That's just the identity. And then here we get the pullback along projection in delta. That's also just the identity. So this is the identity. And this gives us our inductively defined norm map.
Is satisfying base change. There's really no, structure, because this is happening in the infinity category, not some underlying one category.
So base change means that for every pullback square, if you, it's property, it's not structure.
So there's a preferred map, which is
Exactly. There's always a preferred map. There's always a preferred map which goes from here to there, and you define it using, it's some kind of Beck-Chevalier map using the units and co-units of these adjunctions. Yeah. The inductive bit is that if Q is n truncated, then the diagonal will be n-1 truncated. So you will go down one truncation level lower, and then we have to find it already for all the n-1 truncated things, and that allows you to make this definition. Yeah, if you would write it out, I left out some of these details regarding this inductive procedure, but yeah, that you would have to do to make it precise. Yeah, and this definition captures all these examples that we have seen. So let's for example talk about just ordinary semiadditivity of an infinity category. In that case, what we would do is we take A, so curly A, to be just the ordinary category of finite sets. Given that C, we define our functor from fin up to infinity categories to be the functor that sends a finite set S to C to the S. And in this case, let's just see what happens if we take, for example, Q, the map from the 2-point set to the 1-point set. In this case, Q upper star will just be the diagonal functor. It goes from C, which is C to the power of the points, to C to the power of 2 points, which is just C times C. And it's really just sending an object little x to x comma x. And then the left adjoint of this is just going to be the co-product. And the right adjoint of this is going to be the product. This is essentially by definition of what co-products and products are. And then you have to write out what this construction does, but you can check that it's actually precisely this map over there. And then, yeah, the same sort of works for all these examples. If you now look at what equivariant semiadditivity is, the norm maps that you use to define this are basically precisely constructed in this way. In how you have semiadditivity, this is like by definition how Hopkins and Lurie set it up. And also these equivalents you can obtain in this way. So it covers sort of all these examples. Okay. Let's see if I wanted to say something more about this.
So you have this category Q.
Yeah. Yeah, that's right. So in many of these examples, Q is going to be everything. So in case of finite sets, we have sort of addition maps along every map of finite sets is the idea. Also for finite G sets, you would have that. An example where Q is different would maybe be in the global setting, where your A sort of remembers functoriality along all the morphisms of groups, but then maybe you only have transfers along like the faithful morphisms of group power, like the inductive group power morphisms. That would be an example where they're different. Another example where Q is different would be in this category of sheaves. Their A would be all topological spaces, and then this Q would only be the finite covering maps. But yeah, in a lot of examples, they are actually just the same somehow. Yeah, and also this one, they're also both A and Q are just pi finite spaces or M finite spaces for a fixed M. Okay. So now we know what this notion of, this very general notion of semiadditivity, but the motivation for this story was that we get a lot of structure for free. these commutative monad structures. So now the next question is what is the analog of those structures in this parametrized setting? That's what I want to discuss next. So first, let me recall the notion of a span category. I will use a variation of the span category which has right pointing morphisms in Q. So what is this? It will be, well, let me just give the informal description of it. The objects are objects X inside A, and the morphisms are going to be spans So spans are diagrams of this form where we have some object together with a map both to X and to Y. So the source of this span is X, the target is Y. And then we need the additional condition that this right pointing morphism is in our selected class of morphisms Q. And how do you form composition? Well, it's given by pullback. So you have another span, and then you would form this pullback. And this is not uniquely defined up to, this is only unique up to isomorphism, so you need to be a bit careful about how you turn this into an infinity category. But this has been done, for example, in work by Barwick. Yeah, maybe let me explicitly write this composition.
They usually think of these spans of giving you like transfers on pre-sheaves, but then Q would be on the other side.
So it depends a little bit on conventions, I think. I prefer to draw it this way to sort of think of it as this is the contravariant direction and this is the covariant direction. So for example, let me define. So let me define what is.
In span, well, there's, I think French people talk about span beginners.
Yeah. So a relevant notion of commutative monoids that you can consider in this setting is going to be the notion of a sheaf with transfers. So it's going to be a functor from this span category. To, let's say that we just take, for now, just sheaves in the infinity category of spaces. But you can, in principle, just take it in sets or in spectra or other indexing categories. And then you ask that the restriction to the contravariant direction, which is a functor from A up to spaces, is a sheaf. So I didn't really mention any Grodnik topologies, but depending on context, it will be clear what sort of you mean by sheaf. So let me maybe do the explicit case of finite sets, for instance. So example, if A equals Q equals fin, this is just, what I'm talking about is product preserving maps. We have product preserving functors from the span category of finite sets into spaces. And this is the same as a commutative monoid in spaces. And similarly, if you take A to be the category of finite G sets, and you take also Q to be category of finite G sets, then we will get functors from spans of finite G sets into spaces. And then the condition is again that it preserves finite products, which is precisely what a Mackey functor is. So this gives us the notion of a Mackey functor. Yeah, and then this notion of M commutative monads that I mentioned before, this notion by Harpaz, is also an example of this. It will be A equals Q equals M finite spaces. And then you get functors from the span category that you ask to preserve M finite limits. So it's a larger condition, not just finite products. So this gives M commutative monads. Yeah.
The covariant part of X is in C.
I mean that I have in mind a Grothendieck topology on A, and it's a sheaf with respect to the Grothendieck topology. But this is, yeah, that's a general notion in which we define this. It depends a bit on, like, yeah, it's the same word of the word, same use of the word sheaves there. It's the generality in which we happen to define the framework, just to make sure it also applies to cases where you have interesting Grothendieck topologies. But for a lot of these examples, they are sort of just a disjoint topology, where the sheaf condition amounts to preserving products, or here it's some kind of effective epimorphism kind of topology, where the topology also amounts to just a limit preservation condition. So the main, I wouldn't say main theorem, but like one major consequence of what we do is that we show that every Q commutative, Q semi-additive, such a parametrized category, admits an enrichment in these sheaves of transfers. Sorry?
Star Q lower shriek.
Yeah, roughly speaking, yeah. I mean, you use the lower shrieks, and you use that the lower shrieks are the same as the lower stars. Like it's similar to the formula I wrote for the sum f plus g at the very beginning, where you sort of have a canonical way to map to the product, and then you use that the product is coproduct, and you have a canonical map. And in a general setting, you would sort of map to Q lower star, Q upper star, and then use that it's the same as the Q lower shriek, Q upper star, and then use the co-unit, and that gives you the canonical transfer map. Yeah.
So what does it mean that C is a functor?
So what I mean is that, that's a good question. Okay, so yeah, what I'm been doing a bit implicitly is that to set up this formalism formally, and to prove a lot of these statements, you want to think of these objects as individual infinity categories, and it turns out you can do a lot of infinity category theory with such sheaves of infinity categories. So you work basically with the category theory of sheaves of infinity categories, and then what this enrichment sort of means is that we have the functor C op times C, and then there is let me underline it, there is a parametrized hom functor, the hom in C, and then this admits a unique lift. I mean, unique if you ask for certain Q, like compatibility with the Q semi-additive structure there, to two sheaves with transfers. So to make this precise, I would have to tell you much more about how this whole formalism is set up, but I fear that there will not be enough time in this talk to explain all the details. But I'm definitely happy to explain more about this after the talk. But it's similar, like, yeah, so, and this is actually a good point. This is really a consequence of another theorem, which is some kind of universal property. How do we do this usually in the non-parametrized setting? For example, yeah, so if everything was non-parametrized, what you say is, this is semi-additive. Maybe we fix one variable, then we have a functor from a semi-additive infinity category into something that has finite products, and then it uniquely lifts to commutative monoids inside spaces. Forming commutative monoids is sort of right adjoint to forgetting that something is semi-additive. And we proved analogous results in this parametrized setting. Let's think how I want to formulate this, because there's sort of, maybe let me just state it in terms of just these three sheaves of transfers which I already introduced. So working in this setting of parametrized category theory, we can say that there is a parametrized category of sheaves with transfers, which doesn't only consider the category of these objects, but it also remembers for each slice the notion of sheaves of transfers you get on the slice of A over an object. And this parametrized category happens to be presentable in some technical sense, and it's the free presentable parametrized category that is Q semi-additive. Sorry, when I say category, I mean infinity category. And this, in turn, is a consequence of a universal property of span categories. So what we can do is we can consider a category A, and we can consider the parametrized category which assigns to every object X the span category of the slice Q over A. So this is the category of all morphisms that are in Q whose target is A. And you can form the span category of those. X. So if you would do this in the equivariant setting, for example, and you would take X to be the point, you get finite G sets, but if you take it to be G mod H, you get finite H sets. So this collects all the category of finite equivariant things into a single parametrized category. And the statement is that this is the free Q semi-additive parametrized category. Free on one generator. Free on one generator. So yeah, maybe I should spell out what it means. So it means that for any other Q semi-additive parametrized category D, the collection of functors from this parametrized span category into D that preserve the Q limits or co-limits, I mean, basically that are compatible with these Q lower streak or Q lower star functors, is equivalent to D itself. So you can write down the parametrized functor category over A, which is, it consists of Q semi-additive functors from this parametrized span category that I introduced over there to D. And then you can evaluate this at the identity maps that you have. They're always in Q, which gives you a functor into D. And this is an equivalence. That's sort of the precise formulation of what it means to be free on one generator. So this is actually the main result in the paper, I would say. The rest, I mean, there are some more things you have to prove. For example, this sheaves with transfers that is equivalent to sort of the parametrized notion of commutative monoids. But let me focus on this result for a moment. Yes, you can. Yeah.
That's as a full subcategory of A over X, because it's inherited Q.
That's right. Yeah, it's a full subcategory, but it's equivalent to, yeah, it's a full subcategory because yeah, but it turns out the errors are automatically in Q because of the closure on the diagonals condition. So the two subcategories are the same. They're the same. They're the same. Yeah. Yeah. So this is also actually the slice of Q over X. Both interpretations are. Yeah. 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 Let me maybe make a comment about why, like, how we can prove this. So our proof is a generalization of Harpaz's proof in the setting of higher semi-additivity. And the idea is that we prove this by induction on the truncation level of Q. Because every morphism in Q is truncated for some n, in the first step, we're going to reduce to the case where we fix an n and we ask that all the morphisms are like specifically truncated up to level n. And then in the case where n equals -2, in other words, if all the morphisms in Q are equivalences, then it's sort of trivial result because this category is just a point. Like each of these categories are just trivial. And then on both sides we just get D. So now we have to do the inductive step to go from n-1 to n. And this is actually very technical. But the idea is so we are given a certain functor out of the Q, the n-1 truncated morphisms in Q, and we have some functor into some D, and we have to extend it, I guess parametrized. We want to extend it to here, and you have to do this via an iterated left and right Kahn extension procedure. And then you have to check a bunch of technical conditions to make sure that in this process you still remain in this class of functors that preserve discrete co-limits and limits, and you have to make sure that it's actually unique. Yeah, so I say left and right, it's because you first extend to an intermediate category using left Kahn extension, and then you extend further using right Kahn extension. But I'm afraid I won't manage to say in much more detail how this proof is going to go. So in the last couple of minutes, I would like to talk about some additional applications. So our original interest was actually just in equivariant homotopy theory. The fact that we got these additional applications sort of was a bit coincidence. It turned out that the most convenient setup to prove these results was this generality. But let me first just say what these equivariant applications are. So this result over there, it sort of gives the universal parametrized Q semi-additive category. If you specialize this to the G-equivariant setting, these will be precisely the Mackey functors. So it gives us, Mackey functors have now a universal property in this setup. And since genuine G spectra also satisfy the same universal property, we can conclude that they must be the same. So we recover the spectral Mackey functor description of genuine G spectra. But maybe I should mention some names. So Barbic has thought a lot about this. Nardin, Guillaume, and maybe as a last reference, let me also mention Klaus and Matthew Naumann Noel. And then these methods, because they're not specific to just G, we can also generalize them to the global setting and to the G global setting. So we can also
you get the universal property, you get directly the functor between the two things.
Yeah. So you would have to show independently that genuine G spectra also satisfies the universal property. So you're going to show that independently. This is a whole other, this we also did, but it doesn't follow from any of the results that I just told you. And somehow it seems difficult to do it your way, to just directly write down the universal functor and say that it's an equivalence, because you have little control over the morphism spaces somehow. You don't know, you can maybe compute both of the mapping space on both sides. It doesn't tell you that the map is necessarily going to induce an equivalence. So that's a little bit tricky actually. So what we do is just individually prove separately that genuine G spectra also satisfy the same universal property, and therefore they must be equivalent. We used the symmetric spectra definition.
You can prove that without proving the comparison to spectral microscopy.
Yeah, exactly. Yeah. Okay, you have to first compare it with some other models. There are some steps involved in that process where you first rewrite the thing in terms of other models. Okay, but we also get extensions of this result to the G global setting. So to global spectra. The global Mackey functor description of global spectra was already proved before by Lenz. And we got the generalization to G global, which was proved quite recently, independently also by Putzstück. And then conversely, there are some categories that are defined using Mackey functor description, and now they obtain universal properties. So for example, Kaledin has a notion of Mackey pro functor, which is a definition that you can make for G, which are not necessarily finite, but still discrete. So I'm not talking about compact Lie group or something. And similarly, in similar spirit, you have Nicolaus. Wait, what's the order? McCandless, Nicolaus, Krause, I think. Sorry, let me briefly check whether I'm the reader. But the order is wrong. That's why I was confused. Anyway, sorry. Krause, McCandless-Nicholas, who introduced a notion of quasi-finitely genuine G spectra. Yeah, and I fear I don't have time to say much more about the other applications, but let me just say some buzzwords instead. So a thing that I've already mentioned is sheaves with transfers. So every six-functor formalism will be automatically enriched in sheaves with transfers along like the finite étale maps. Depending on your six-functor formalism, the notion of finite étale might vary, but there is sort of, yeah, transfers for finite étale maps. And then maybe another thing that I would like to mention is in certain character theories, there is a notion of, there is an induced character formula, and we are able to prove a fully coherent version of that using these results. So in collaboration with Carmelli, Ramsey, and Janowski, we do this for higher categorical characters. And Ben Moshe has used the results to obtain an induced character formula in transchromatic character theory. Okay, let me end here. Thanks for your attention.
Questions?
So my contact with this type of thing is mainly through six-functor formalism, where, I notice, it seems to me the big difference is there's no F upper shriek in what you're talking about.
Yeah.
So that's used a lot. These transfers for finite étale maps, we get sort of twisted transfers for proper maps. So is there any interest or reason for expanding the scope of what you're doing here to include something like that?
So a big difference with these upper shrieks is that they have to be provided as additional data. They are not automatically obtainable from just a contravariant punctuality. Mm-hmm. And this story is really talking about properties we can put on such a functor. So it is only able to talk about these left adjoints and these right adjoints. Like, by the way, I'm talking about lower shrieks, but it's a slightly different lower shriek than maybe the one you're used to. Mm-hmm. Because it doesn't encode the proper push forwards or something. It's only sure. Exactly.
Just the F upper stars or F upper shrieks for étale maps.
So I certainly think that it's, so I'm not sure what the question is. It's certainly useful to study six-functor formalisms, but our formalism won't be really able to say much about these lower shriek functors. Yeah, so.
Contact or a way of expanding. But okay.
It is. Really. So there's maybe a fourth application, which is you get universal properties also for certain span 2 categories, and this is actually useful for constructing six-functor formalisms. Mm-hmm. So once you have a functor from, let's say, this A op, or like maybe it's topological spaces or schemes or something, into infinity categories. And you know that for certain maps you have left adjoints that satisfy base change. For example, finite étale maps. And for certain maps you have right adjoints that satisfy base. Maybe I shouldn't have said finite étale, I just mean all étale maps. And for the proper maps you have right adjoints. Then sometimes you can assemble them into like getting these, like this is for example Schulze does in his lecture notes on six functor formalisms. And we can prove using these results that in certain cases there is a universal two category which adds these left and right adjoints and that are compatible. And it is a certain span category. So in particular, if you have these properties, it extends to this span category. And then you can just restrict back to the underlying infinity category where you forget the two morphisms to get your six functor formalism. So, but this is still work in progress, and we are not really able to get the most general case, which is the one that you would want for six functor formalism. So yeah. Hopefully at some point.
You didn't mention compact Lie groups, or you mentioned it very briefly, but so this theory of stable dualizable groups, including compact Lie groups, there could this sort of between the work of Sadowski and Hopkins-Lurie, where we could prove this sort of equivalence in the case where in the Kn local category where the space A was KZN, where the two ends are the same. So one can prove that there's an equivalence like this in that situation, but without inductive. So basically without starting from -2 or -1 connective things, but starting at a certain level.
Yeah.
And I think the thing that made that work was somehow that for this kind of a generalized, this kind of stable dualizable group, the adjoint representation behaved like a zero sphere, so that in the Wittmüller equivalence, the shift one might expect for a compact Lie group was somehow not visible. Are there other? I mean, are there approaches to some?
I mean,
I guess I'm not expecting that there should be a compact Lie group version in this framework.
So in the framework that I've been discussing here, exactly it won't work because the left adjoint is not equivalent to the right adjoint. They agree up to shift. Like up to like not maybe I shouldn't say shift, but like tensoring with some invertible object. There is a framework which can deal with this. This is actually what I developed in my thesis, my PhD thesis, which I called twisted ambidexterity. And that precisely, I mean, it's sort of a parametrized generalization of John Klein's dualizing object. So for every morphism, you get some dualizing object df. You can abstractly define it, maybe in general will be badly behaved, but you get a canonical map from here to here. Now you can ask it to be an equivalence. And then in the equivariant setting, if f, let's say, is just a map from G mod H to the point in G spaces, then this will be precisely this tangent representation of G mod H. And then this is co-induction, as this is induction and this is co-induction, and you get back the Wittmüller isomorphism. But I wasn't aware of any examples where, so you seem to mention an example where this happens to be the unit without it following from this inductive procedure. And I would be very curious to know more about that. Yeah.
Other questions? I'll meet again at 12:00. Thank you very much.
Thank you.